Julia will speak about modular spaces as irreducible symplectic varieties.
Thank you very much. It's an honor for me to speak at this conference in celebration of the work and the birthday. This is the last talk of the day. I hope to try and I'll try and keep it sort of not very technical. It is a technical subject, and it's a subject that I'm learning as I'm writing this paper. So I will try to sort of give more of a general story rather than the sort of results. And the story is the story of a modulized spaces of sheaves on K3 surfaces, and then different kind of generalization. So it started modulized spaces of smooth modulized spaces on K3 surfaces, and you can extend to singular things, but you can also extend the kind of objects that you consider, not sheaves, but other things. So let me start with the work of Mukai. And in fact, this is the JAMI conference, and there's a lot of work of Japanese mathematicians in this talk. So let me just write the modulized spaces of sheaves on K3 surfaces. Of stable sheaves on K3 surfaces are smooth and have a holomorphic symplectic form. Okay, and so let me be more precise. SH would be a polarized K3 surface. I would fix the term classes of the sheets I want to parameterize. And so the statement is that, so here I will assume that this, this thing which I'll call the Mukai vector, and so this just encodes the term classes of the sheets I want to parameterize, and I assume this is primitive. So it's not a multiple of another non-trivial multiple of another element in this lattice. So V primitive, and so H general. And so the statement is that to the Giesecke moduli space, so if M the H of M the H, this is a Giesecke moduli space, the Giesecke moduli space of H semi-stable sheaves on the K3 surface. And so under these assumptions, the locus of semi-stable sheaves is the same as the locus of the stable sheaves. And this is a smooth projective irreducible holomorphic symplectic manifold. And so these were called hyper-Kahler manifolds. So irreducible holomorphic symplectic manifold is the same as what a Rosen's thought was hyper-Kahler manifold. So compact simply connected, and well, in these cases, they're all going to be projective. So I simply connected and with a space of holomorphic two forms spanned by a holomorphic symplectic form. Okay, so this is Mukai, and what are the two ingredients that you need to have such statement? The statement being the stable locus is smooth and has a holomorphic symplectic form. So the first is a little bit of deformation theory. So if I have F, a sheaf on the K3, the tangent space of the deformation functor is canonically identified with the X1, and the obstruction space is strictly contained in the X2. And so if F is stable, in particular it's simple, Hom of F, the endomorphisms of F is one-dimensional, and this is Serre dual to the X2. So Serre duality on the K3. And because of this is a linear space of one-dimensional space and vanishes. So the obstruction vanishes, that means the moduli space is smooth. And what is a holomorphic symplectic form? So if I have a stable point in the moduli space, then the tangent space, not only to the deformation functor, but to the moduli space itself, is this x1. And the symplectic form on this moduli space at a point can be identified with a cup product. And this, again, this is just the cup product, and the sheet is locally free. This is H1 of the endomorphisms, and sort of it's just the regular cup product, and it's not used resolutions. Anyways, okay, and so this is what the holomorphic symplectic form is. And so there are different ways of actually thinking about the symplectic form, and depending on what you want to do with it, one approach is better than another. If you just want to understand what it is at one point, this is sort of maybe the natural thing to do. But if you want to prove that it's closed, maybe it's not necessarily the best point of view. But this will be enough for today. Okay, and so maybe let me give you an example. So F is the ideal shape of a point of a subscheme of length n on the K3, then this chi vector of F is 1, 0, 1 minus n, and the moduli space is just the Hilbert scheme of endpoints. Okay? So, so these moduli space generalize the example of for G key and for Bill. And there's a parallel story for abelian surfaces, which I'm just going to ignore. Okay, so what is a general theorem? So this is the work of many people. So Mukai, O'Grady, Yoshioka, and then I want to add Bridgeland and Bayer-Macri. And then also Hoybrechts. So this is just putting together a lot of work over several years. And it's following. So if, again, B is a primitive Mukai vector, and B squared is greater or equal to -2. So as an element in the homology of the K3, there's an affine intersection pairing. And this is what I mean by B squared. Okay, and so under this assumption, the moduli space, okay, so I need to tell you what moduli space is. So here I'm considering these are for moduli space. And now I want to consider instead something more general, bridge instabilities. And I'm not going to define what these are, but they're sort of a natural extension of the slope stability for coherent sheaves on a curve. And sort of there's a natural sort of way of generalizing this to derived category on a surface and in other contexts too, but for the moment this will do. Okay, and I assume that this, so here up there I have H is general, and here also the bridge instability that also has to belong to a certain connected component. Let me ignore that. Also is general, and I'll say the generic. Okay, and then the statement is that this moduli space, which I'm going to denote, and the sigma is the moduli space of bridge unstable objects with this class is sort of the moduli space sigma semi-stable objects in the derived category of coherent sheaves with a K3 surface. This is non-empty. Earlier I didn't have any non-empty statement, so here I under that condition on v squared greater or equal to -2, this is non-empty, and it's irreducible holomorphic symplectic of dimension v squared plus 2, and its deformation equivalent to the Hilbert scheme of points on a K3 where n is the correct dimension. Okay, so let me make a remark. So earlier we had Giesecke moduli spaces, which are constructed as global GAT quotients of a certain plot scheme, and so in particular they're automatically projective. And in this case, in fact, I should have, this is non-empty, I should have said here, projective irreducible holomorphic symplectic manifold of this dimension. And so here in this more general context, the modulized spaces exist. So the modulized spaces exist as algebraic spaces, but there exists a natural line bundle on them. And so Bayer-Macri. So there exists a line bundle which depends on the stability condition, but in fact depends only on the chamber it belongs to. But anyways, that I guess doesn't matter. But what did I want to say? Oh, there's just a natural line bundle that is strictly enough. And so maybe let me just say, so more precisely, for every E on, or maybe F on X plus S plus T, flat family of sigma semi-stable objects of class B, there's a notion of flatness in this context, then there is a line bundle L sigma on this T that depends on this family. And if T is proper, then I can intersect this line bundle with curves, and this is greater or equal to 0 because I'm considering this semi-stable family of semi-stable objects. This is greater or equal to 0. And I know exactly which curves on T have trivial intersection with this line bundle. So L dot C is equal to 0 if and only if the two general points of on C for C and C prime in C general points, the objects that are parameterized by corresponding to these points, so EC and EC prime, are S equivalent. So they have the same Jordan-Holder filtration. They're both semi-stable. They have the same isomorphic associated graded pieces with respect to the Jordan-Holder filtration. And so on when I go to the moduli space, I'm identifying all the S equivalent classes, and so the line bundle becomes strictly S. Okay. And maybe another remark is that and this again is Bayer-Macri. So for any sigma and tau V-generic bridge instabilities, the corresponding moduli spaces are birational. And conversely, any smooth K-trivial model of these moduli spaces, smooth projective K-trivial model of these moduli spaces is of this form. So this gives maybe one motivation for introducing these more general moduli spaces, because it includes all the birational models of these moduli spaces. Okay, so all this was under the assumption that V was primitive, and so the stable locus, which is smooth by Mukkai's theorem, is the whole thing, and so they're smooth and projective. So what happens when we remove that assumption, so that we have singularities. And so the situation is still pretty good. So what happens if V is primitive? Now, V0 will be a primitive, and M will be greater to 2 an integer. Okay, and so there are two cases. In the first case, M is equal to 2, and V0 squared is equal to 2. Okay, and then you see that the dimension of the moduli space in this case is 10. In this case, then by O'Grady, Glenn-Sorger, and then so the moduli space, I'm going to, and maybe if I consider bridge stability, I also want to write Nietzsche this earlier work was only for these for moduli spaces. And so this is a singular symplectic variety. And I'm going to define the symplectic varieties in a second. But the statement is that there exists a symplectic resolution. This is 2V0. There exists a symplectic resolution. So you can sort of study how the singularities of this thing look like, and if you blow up the single locus with the induced reduced scheme structure, it's smooth, and the symplectic form extends on this whole resolution. And this is in the deformation class, O'Grady test. So one of the two sporadic examples that we had. So what happens in the other case? So for any other case, so whenever M and V squared are not 2 and 2, then here now the people that I should write are Palladi and Sorger. And I also Bayer-Macri-Neuer-Perry-Stellari. Then these moduli spaces, these are non-empty projective symplectic varieties and moreover what do I want to say? Oh yeah, they're locally factorial. In fact, this thing here implies that there exists no symplectic resolution. Because a symplectic resolution has to be a semi-small map. So if the singularities are factorial, the exception locus of resolution is divisorial, but the singularities are in hyperdimension, and so you can't have a resolution that has an equal to divisor that contracts too much. And they are singular, and yeah, so singular in codimension. Because as soon as this thing is not empty, then you pick something here, and then this element here is going to be in the singular locus of so the non-empty statement that I will keep sort of carrying over all comes out of the case. Yes, the rational Lorentz, yeah. And in fact, so what is definition? This is about definition to Bavilla. So X normal is called the symplectic variety if let me say in the sort of more let me write down this, if there exists a holomorphic reflexive form, a reflexive holomorphic symplectic form. Okay, I just mean that the smooth locus has a holomorphic symplectic form, and if there exists a reflexive holomorphic form which extends to a holomorphic form on any resolution of X. Okay, so the smooth locus of X has a holomorphic symplectic form, and then when I resolve X, this symplectic form is defined in an open subset of this thing, and it extends to a holomorphic thing. And so, in particular, rational Gorenstein. Okay, so in the smooth case, there is the theorem of Bavilla and Bogomoda, which states that if you look at compact Kahler manifolds with C1 equals to 0, then up to a finite cover, they break into a product of abelian varieties. These are reducible holomorphic symplectic manifolds, and these strict Calabi-Yaos. So there's been a lot of activity recently to do a singular version of the Bavilla-Bogomoda decomposition theorem. And so let me remind you what this is. So, and this is the culmination of the work of many, many people. I think, I hope I have I've written all the right names. So Druel, Greb-Guenancia-Kebekus. And Horing-Peternell. And there's also Kahler version of this, but I'm just gonna state it for a projected case. The Kahler version is by Bayer-Lahoz-Macri-Neuer-Perry-Stellari. So X normal projective variety with KLT singularities and numerically trivial canonical class. Then there exists a finite cover, which is étale in codimension 1. So X, so there exists this quasi-finite étale cover, quasi-finite means this. This breaks into the product of a Boolean variety factor and then a product of irreducible symplectic varieties and a product of irreducible Calabi-Yau. Okay, so let me tell you what these things are. Excuse me? Yeah, absolutely. So this is smooth. Okay. So let me tell you what the definition is. Okay, X normal and projective is called irreducible symplectic variety. If it is a symplectic variety, in the sense of Bavilla, so with this reflexive symplectic form sigma X, and furthermore, for every gamma from Y to X, finite cover, étale in codimension 1, the algebra of reflexive holomorphic forms on Y is generated by the reflexive pullback of this symplectic form. So it's not only a condition on X, as in the case of the smooth things, but you also need to check all these finite quasi-étale covers. And so let me give you an example and a non-example. So if X is smooth, then it's an irreducible symplectic variety if and only if it's irreducible holomorphic symplectic manifold. So it really extends the definition in the smooth case. And the non-example is if you have S, a K3 surface, and you look at the symmetric product of the K3 surface, then it's not irreducible because the quotient map, right? The symmetric product is defined as the quotient of the symmetric of this by the symmetric group, and this is quasi-étale because S is dimension 2, and so this property does not hold for this. And so you see also that this is not a birational invariant property because this thing here has a symplectic resolution, which is the Hilbert scheme. right? So this is irreducible holomorphic symplectic manifold, and this is not irreducible in this term because there's this finite method. Okay, so in the context of these moduli spaces, so what is the statement about these singular moduli spaces? So, prego la pagnetta. So these M B0H, so if they prove it in the Giesecke case, are irreducible symplectic varieties. And moreover, their deformation class, the deformation class of these objects, depends only on M and the square of the primitive Mukai vector. So in the smooth case, in any given dimension, which depends only on this, they're all deformation equivalent. And in the singular case, you need to consider this integer too. So my goal today is to extend this and in fact also the theorem of Kahler-Sorger, this part here, to not moduli spaces of objects on K3 surfaces, but to moduli spaces of objects, certain kind of special objects on cubic fourfolds. So more precisely in the Kuznetsov component of a cubic fourfold. So let me remind you that so there are certain so holomorphic symplectic varieties associated with cubic fourfolds. Okay, so X now will be a cubic smooth cubic fourfold. And so let me just briefly remind you that sort of there are many to X. One can construct many hyper-Kahler manifolds that that you associate with X, and you can think of it if you want of some kind of invariance of X. And sort of what are the classical examples? So f of X, this is the variety of lines on X. This is Bavilla and Donaghy. And this is in the 80s, I think. And then V of X. I don't want to be precise, but this is constructed starting from the moduli space of twisted qubits on X. It's not really equal, but and sort of this is dimension 4, this is dimension 8, and they're deformation equivalent to the Hilbert scheme of points, the right number of points on a K3 surface. Okay, so sort of here in both cases, these are parameter spaces for curves on X, and sort of somehow there's these two different approaches, if you want, for constructing these hyper-Kahler manifolds from cubic fourfolds. If you want a sort of, I would call it cycle theoretic approach. And then moduli theoretic approach. And as is often the case, there are certain things that come out better in one case and some certain other things that come out better in the other approach. And I would say that anything that has to do with the homomorphic symplectic form and extension of forms is better in this case, whereas maybe studying the singularities of things is better in this case because you have deformation theory for sheaves and sort of it works out pretty nicely. And in fact, in certain cases, the objects that are obtained in one way are also obtained in the other, but not always. Okay, so let me tell you a little bit about the modular theoretic approach. And as I said earlier, I'm just learning these things, so I'm not really an expert. So Kuznetsov proved that inside the derived category of coherent sheaves on X, there's this admissible category, subcategory U of X, which is defined as the objects in dBx that have no non-trivial hums, if you want X P. So the hums are 0 for every P and Z from 3 line bundles. So I have no hums in any degree from O of 1 and from O of 2. Okay, and let me give you an example of something that satisfies these vanishing conditions. And this is the easiest example that I know. And so, for example, if I take a hyperplane section of X and I call the embedding I, and I take E rank 2, so maybe let me call it F, vector bundle on Y, say a smooth hyperplane section with Chern classes C1 of F equal to 0 and C1 of F equal to 2 times a class of a line. And then the sheaf E, which is just a sheaf F, but U is a sheaf on X, this satisfies the vanishing conditions. So this is Druel. I think it's Druel thesis. Okay, and sort of again, this is Kuznetsov. So if X is, for example, a Fafian cubic, then so if F is a Fafian cubic, Bavilla-Donaghy had already showed that there exists a K3 surface naturally associated to it with some nice geometric construction. I don't have time to discuss it. And so Kuznetsov showed that when X is a Fafian cubic, then there's an equivalence between the Kuznetsov component of X and the derived category of S. And similarly, when X contains a plane, there's also a naturally associated K3 surface. You project from the plane, you have a quadric bundle, and the set of rulings, and in the quadrics is a K3 surface. And now the Kuznetsov component is not isomorphic to the derived category of S, but of sheaves, derived category of sheaves twisted by a non-trivial Brouwer class. But just to say that when the cubic fourfold becomes special in a certain sense, and you can make very precise meaning of this, then this thing here is the derived category of a K3 surface that is associated to S. And what is the key ingredient of, not the key ingredient, the key property of this Kuznetsov component, and this will be the key ingredient in the rest. And so the key property that there exists a surduality functor just like that is the shift by 2. Actually, let me just say it. So the key property is that the hums between 2 objects, E and F, the hums is dual to the hums of, I change F and E and I shift by 2. And so the hum is dual to the X2 and et cetera, et cetera. And sort of this is, so surduality behaves like in a K3 surface. And sort of once you set up deformation theory for these objects, then things behave exactly like you are on a K3 surface. And so the smooth locus, so maybe Kuznetsov and Markushevich, the modulized spaces, objects in the Kuznetsov component of that of stable moduli spaces. Stable objects in the Kuznetsov component are smooth and have a holomorphic symplectic structure. Exactly as in Mukai's theorem, or rather a generalization of Mukai's theorem to this context. And in fact, if you're dealing with sheaves like in that case, then you don't need to go to Bridgeland stability conditions. You have just a regular slope stability for those sheaves, and then you can even write down what the holomorphic symplectic form for X1 cross X1, and sort of you can write it down explicitly what the holomorphic symplectic form is, and this is what Kuznetsov and Markushevich do, and then they generalize. Okay, and so by the work of many people, so Bayer, Macri-Stellari, then they show that there exist Bridgeland stability conditions on this Kuznetsov component, and they recover. So Lee, Tuzi, and then Lautz, Len, Macri, and Stellari, they recover both the Fano variety of lines and the twisted cubics as modulized spaces of objects in this sense. And in fact, for this, you need to assume that the cubic fourfold did not contain P2, and it was kind of maybe a mystery condition when you view it just as twisted cubics. But in this case, you actually see very well why there are singularities in this case. But this may be a side remark. So let me write down a theorem. So there's a breakthrough in sort of this world that happened a few years ago with this paper with 6 authors. So Bayer-Lahoz-Macri-Neuer-Perry and Stellari. And in fact, it was, while trying at least to read this paper, that I realized some of the things that I will discuss today. And so the theorem is the following. So you consider a primitive Mukai vector in the Grothingy group of this derived category. So maybe primitive. And sigma V generic stability condition then the statement is that these modulized spaces are projective, reusable homomorphic symplectic manifolds, deformation equivalent to the Hilbert scheme of endpoints on the K3 surface of dimension. And here again, there's a Mukai pairing. I need to assume there's this condition. So non-empty. Okay, and so as a corollary, they were able to deduce that they understand exactly when this Kuznetsov component is isomorphic to, is equivalent to the derived category of a K3 surface, so some K3 surface S, if and only if X lies in one of the Hassett divisors CDs, where D sort of satisfies certain incongruence, which I'm going to ignore. But the upshot of this is just that the locus where this holds is dense on the moduli space of cubic fourfolds. So you have these countably many intergalactic divisors, and D has to satisfy certain congruence condition, but they're infinitely many and they're still dense. Okay, and so maybe let me write down here. So I'm writing it down. So B0, not over gradient 10 type. Assume that B0 squared is greater or equal to 2, and sigma is B generic. Then these moduli spaces, so then the sigma is this is non-empty. So this is a projective, normal, and connected. It's an irreducible symplectic variety in the sense that I discussed earlier, and it has locally factorial terminal singularities, but it's not smooth and it does not have a symplectic resolution. And lastly, the deformation type and the homomorphism class is uniquely determined by, as is previous case by the integers m and b zeros. Okay, so I was planning to give a sketch of the proof, but I've run out of time, so I can answer questions.
Questions?
Okay, in this, I don't know. In the smooth case, yes. Yes. Okay, actually, no. Yes, yeah. Yes, absolutely. And so all the plots are related to a wall crossing. Yes. Yes, yes. So certainly. Right, yeah, so certainly you have finitely many different rational models that are related by plots, but then I don't know if so certainly the movable cone has finitely many chambers. Yeah. Okay. Yeah. Okay. Yes. Okay. Yeah. Okay. Yeah. No, this is no. Yeah. Actually, I have. So one ingredient in the thing in the smooth case is that you identify the H2 of the moduli space with the orthogonal complement of the Mukai vector in the homology of a K3 surface. And so then you understand, what the rays are and all the stuff in terms of this. And so I do have a statement about this for these moduli spaces, which I didn't write down. But this relies, yeah, I haven't thought about that, but it's plausible that the same. Yeah, it's yeah.
Other questions or comments?
Yeah. Yes, because so it's I didn't say when you have X, you look at isotropic classes in this sort of so there's some kind of generalization of the Mukai lattice, which I'm going to denote like this. And you look at anyways, you can look also just at the growth and decay of the derived category, and you look at isotropic classes, and you take the moduli space with respect to this isotropic class, and then that is a K3 surface, because the square is 0, so this is dimension 2, and this is a K3 surface. And then they use the fact that this is a moduli space of objects on this thing to relate the derived category. So now let me call this S, and then they relate the derived category of S with this, and they prove that the natural Fourier-Mukai transform given by the universal family or the quasi-universal family determines an equivalence between the derived category of S and this thing here. Addington and Thomas, they only had it on an open subset of these things here. So how they proved it was they intersected it with I think it was C8, and then they proved it on that locus, and then they were able to deduce that it held on an open subset. And so this tells you that it holds for every X in the CDs, not just on an open subset that contains a C8. And so the reason why I mentioned this corollary is that in the proof, you use the fact that you deform the cubic fourfold to this locus, and then you deform the moduli space. So this is why I mentioned it.
No more questions or comments, but